roof's gonna fall.
I was sitting on the chairs like on that side of the building, like outside, and like the metal structure just started shaking like crazy. Thought it was gonna fall on me. It was crazy. But I had fun.
So you thought you were gonna die. That's interesting. So now the rest of your life is cake, is icing, because
Wait, I'm so stupid because why did I just sit there? I was just like,
well, it's deer in the headlights syndrome. It's paralysis. It's a human thing.
but I thought I would be better.
I mean, what could you do? You're gonna stop you. You gonna stop you. Stop.
Like go under the bed, some.
Oh, I see.
I just stood there.
I was teaching, and my phone had this alarm 3 seconds before the building shook, right? And then everybody looked at me like, "Do we get?" I'm like, "Yeah, get on your tables." So I was like under the table, and I was checking the earthquake stuff on it, and it was like, anyway, that's like the third earthquake I think I felt since I moved here in 2005. Yeah. So it's fine with me. I don't need any. But it was pretty strong.
Yeah.
Very quick,
Yes.
but pretty strong.
Yes.
Yes. Huh? Which? Oh no, I'm not saying yesterday was like really like the strongest, but it was pretty strong.
And you always get alerts and it's like, oh, there was an earthquake. I'm like, girl, there was not an earthquake. I did not feel that, but that was an earthquake.
That was yes. Well, very often it depends on where the epicenter is. It depends on what the density and so forth of the land between you and the epicenter is. There's all these kind of things about did you feel it or not. There's a whole website devoted to did you feel it. I think it's in Julian, right? Epicenter was in Julian. It was like 2 miles south of Julian, I think it was. Yeah. Anyway, sorry. Sorry. I just wanted to get that out there because I was in the room next door when it happened.
You spoke.
I was in the room when it happened. The room when it happened.
Is that in the book?
No, it's Hamilton.
Oh,
I'll tell you that.
There you go. Yeah. Of course, it's the room where it happened. This stuff. All right. I'm sorry. I just was curious to get that out there because it's a shared experience we all had.
what's the statistic on how you felt it? No question.
What's the probability that the next one is the big one if we all go floating off into the?
No San Jose.
That wouldn't be too bad. For sure, float up to Canada.
I knew I'd survive.
No, it's wait,
Yes.
Is there like an aftershock sometimes after?
Oh yeah, there were aftershocks. They were just so minimal. I don't think anybody here felt them. Yeah. Okay. Okay, that's my point. I derailed everything. It just came to mind. So, what we're about to get into is related to the fact. All right, let's say has anybody ever seen the movie Arachnophobia?
Yes.
Okay, and if you haven't, I don't blame you. Spiders are kind of like a big, I'm not phobic, but I definitely don't like spiders.
What about eight-legged freaks?
But what now? Oh, Eight-Legged Freaks is awesome. That's an excellent movie.
Oh yeah, definitely.
That's a beautiful tree. Bring it off and just enjoy the shit out of the movie. I love it. Alright, sorry. Let's say we go to an island and we discover a new species of spider. Yes? The first one we see, do we have any clue when we first see it if it's representative of the average size or whatever?
No.
Do we have any idea the range of sizes of the species of spider? No. So we do not know the population mean, nor do we know the population standard deviation. Yes? Every damn thing we've done so far with things has basically involved us knowing those two things. Would you agree? Very few times we have never done a lot with a situation where I didn't know those two things. Does that make sense? Is everybody with me? Okay. So what we're gonna do today is we're gonna take 2 steps. We're gonna first say, all right, let's be honest, most of the time we don't know the population. So what happens then if I want to get an estimate for the population? How the shit exactly does taking a sample lead us to an estimate for the population mean? Because if I take a sample, how much money would you put on its mean being the exact same as the population?
Nothing.
I would put nothing. Right now I'm a teacher, so I wouldn't bet much anyway, no matter what the proposition is. but I don't think anybody would put much money on that. Are you guys with me? If the bet was they're not the same, I'm putting a lot of money. And again, I'm a teacher. How are we all doing? Okay. There are, so, what do you think? It's gonna be a better example, Jeff. No, I'm gonna just go with the one that came to mind. Let's say that, yeah, all right, let's just stick with the spiders, Jeff, sure. Let's say that there's this island and there's this little part here that's never been explored, yes? And let's say that we know the mean, how do you measure a spider? Let's say these spiders are roughly circular, so the mean diameter of a spider is like, let's say, 5 centimeters. Is everybody kind of with me? And the standard deviation is known to be 1.2 centimeters. Okay. So this spider on this island is been cataloged. We know this, but there's this one little section we've never explored, but it's still part of the island. Yes. But that one little section has like a lot. Like for some reason, it's really heavily forested. It's got a lot of freaking insects. It's got all this shit. So we're like, okay, let's go in there. Let's take a sample of the spiders from that region. We're curious if it seems their mean is different. Like we might think that their mean size might be more because there seems to be a lot of resources there. A lot of food for them. You guys kind of with me? All right, so insects and stuff from humans. So, again, we go in and we take a sample. Let's say we take a sample of, what's a good sample size?
25.
Why is that not a good sample size?
Because it's too small and it's not, whatever. 34.
34 is beautiful. Because I want to be able to do things with my sample that leads me to say it's normal enough. So my sample size has to be greater than 30. So since this is the same island, it is safe to assume that the standard deviation of these spiders will still be 1.2 centimeters. I'm just curious if in this little region they might have a higher or lower average diameter. So again, just to remind us, we're taking 2 steps into reality. Everything we've done so far has been a little idealized. Because when we analyze something brand new, we don't know shit. And everything we've done has been assuming we knew this mean and standard deviation, right? Most often, we don't know shit. Hey, go look at the contamination in that pool. Well, I know. No, you don't know shit. Go take some samples. I don't know anything, right? So we want to get to the point where we don't know mu and we don't know sigma, but we're going to take 2 steps. We're going to say, okay, let's pretend like we do know sigma. And there are situations where that does happen. We know sigma. It's just a smaller subgroup of the whole thing that I'm curious, well, what about this section? Yes. How we know so far? So we want to do 2 steps just because taking both steps at once is too much. There's a lot going on. Okay. Plus, there are situations where this is true. So this is the mean for the whole thing. I'm curious about the mean just for the sample I took, for this area. Yes? And let's say the mean I get here is, what are you going to say, Jeff? 5.3. Now let me ask you a very important question. If what I thought was the mean of the spiders in that area is different from 5 centimeters, can I just stop right now?
Wait, say it one more time.
My thought is, I think the mean of the spiders in that region, the mean diameter, because they're basically circular almost for these spiders for some reason, neat little sort of spiders. I think the mean is different from 5. And didn't we just, what did we get for the mean?
For this one?
What did we get for the mean? No. What do we get for the mean from our little section?
5.3.
So why, I'll just say it like this, why can't I just stop there and go, there you go. I'm done. I showed it. Can anyone tell me why, just everybody agree, 5.3 is not equal to 5?
Yeah.
So on one level you might think, well, you're done. You showed it. Yay, now stop playing with spiders, right? You guys kind of with me?
Yeah.
I cannot do that. I can't. Was my claim about the 34 spiders I took, or was my claim about that whole region?
Oh, the whole region.
Is it possible I just happened to pick a sample of bigger spiders? Could that have happened randomly?
Yeah.
Could I, if I just go pick students, could I randomly pick older students?
Yeah.
And therefore, any average I take would of course be bigger than the actual average. Is it possible?
Yeah.
Is it possible I actually took smaller spiders?
Yeah.
Well, right, so I can't, if I ever get information from a sample, that by itself is not enough to prove anything. If I'm trying to say, let me see if you guys are with me on this. I can't remember, what's weird is I don't think I said something earlier, which I think I did maybe. What does standard deviation do for us?
Tells you how many points away the mean is.
And if I want to say it a very layman way, just to talk about it conversationally, it gives me a unit of measurement. It gives me a way to measure things. If somebody's height was 3 standard deviations above the mean, would that be freaky?
Yes.
Good. I don't even have to tell you what their height is. If it's 3 above the mean, they are unusually tall, yes?
Yes.
So a z-score uses standard deviation to kind of measure how different things are. So if my claim is the average spider diameter in this little section of the island is more than 5, I have to calculate a z-score to see how really different they are. If the z comes out to be 0.2, is that very different? 0.2. If somebody had a z-score of 0.2 for a height, would you go, holy shit, look at you? 0.2. Are they very different from the actual average? No. You're not going to say, holy shit, you're 5'10", look at you, mountain of a, no. All right, man, you guys good? I really want this to make sense. 5.3 is bigger than 5, great. But that's just a sample. Not only does it have to be more than 5, it has to provide evidence that every spider in there is more. So what it has to do then is it has to be far enough above 5. And what measures distance in statistics? Z-scores. Standard deviation set the unit of measurement. Z-scores measure the distance. Okay, maybe. So what chapter 8 is doing is it's putting together a lot of everything we've done. It all comes together in one process. So the very first step, chapter 9 is actually hypothesis testing. Chapter 8 is sort of like a first step. Chapter 8 kind of says where. All right, let me ask you this question. What is it that we don't know about the spiders here that we want to know?
The standard deviation for your sample?
No.
No.
We're going to assume it's 1.2. Because they're still on the same island. We already know it's 1.2. We don't know their average. What's 5.3?
That's the mean.
That's the mean for 34 spiders. And do you agree? Let me just say this is a really big island. Would you agree there's probably more than 34 spiders? What do you say?
Yeah.
I don't know, Jeff, why don't you go there, take some pictures? Go to your little island, we'll wait. All right. Every time I do this, I do it in a different way because there's a lot of parts to this, but how's everything so far? So if I take a sample by itself, that's not enough evidence of anything.
Yeah.
I do not know. So here's what I don't know. I know the mean of spiders in this part. I don't know, get out of there, mu here. I know 34 spiders from that region have a mean of 5.3. What I want to do is I want to be able to say something like, the average diameter of spiders in this region is somewhere between 4.9 and 5.7 centimeters. I want to be able to say that. I want to give a range within which I'm that confident that the actual mean is. You guys know? The only way to be 100% confident is if I say it's somewhere between 0 and infinity. Is that useful? No. So that's why we always have this kind of like, if I say I'm 95% confident it's between 4.9 and 5.7 centimeters, what's the probability that I'm kind of implying that I think I'm wrong?
Pretty high chance.
95% chance, I'm 95% confident that it's from 4.9 to 5.7.
Oh, you're
Inherently, I'm saying, what's the probability I'm wrong?
5%.
5%. Is everybody with me so far? Yeah. And a 5% chance of being wrong, I don't know about you, but for me, that's good. For any human, I mean, definition of being human is making mistakes, so that's one definition. So a 5% chance of being wrong is pretty good. In fact, 5% is what we call unusual, remember? Yeah, like, I'd much rather go to surgery where I have a 95% chance of surviving versus 50% chance of surviving. Yes, so 95 is really good. Okay. So here's the idea. So everybody with me? So we don't know the population mean of the spiders in this region. We don't know that. Do you all agree it exists somewhere? So let's say this is from 0 to whatever. Do you all agree that the mean of the spiders exists somewhere? That it's just somewhere. Sort of like the average left foot size of all gross foot students. It is a number. It exists. Yes?
Yeah.
Okay. So all this is trying to say is that mu is somewhere. It's a number. It exists. At a given time, if I was somehow magically able to get all the measurements of every spider in that region, I could get the average of the population of the spiders in that region. You with me? So it exists. What did we just say earlier about any X bar I get? I'm pretty certain it's not going to be this. So it's going to be somewhere different.
Oh, because X bar is the sample mean, not the overall mean.
Let's see. If I want to be 95% confident that the actual mean is between this number and this number, how many steps out roughly? We're going to get it better because this is an estimate, but how many steps do you have to go to catch 95% of the data? 2 steps. But we normally would use the mean, but that's exactly what we don't know. Now I want you guys, do you see how I've drawn this here? In reality, we do not know what this is. I don't know where it is. So in reality, all I really have is this. But if I go about 2 steps up from this and 2 steps down from this, how much data would I have caught? 95%. So then how confident would you be that you caught a specific value? 95%. Sort of like I hate, all right, I like fish to look at them. I do not want to eat them because they taste horrible. Right? If I smoked and eat fish, I probably wouldn't have any money because those are pretty expensive. So thankfully I don't do either one. If I went to a certain pond and I threw out a net and caught 95% of the fish in the pond, how certain am I that I caught this one fish named Billy that I've been trying to catch since I was 7? If I catch 95% of the fish in the pond,
You're 95%.
I'm 95% confident I caught Billy, yes? Yes? Okay. So let me stop for a moment. So if we don't know mu, what is our next best guess? How do you estimate mu? X bar.
Yeah.
X bar, if that's all we know, that's our best guess for the mu. Yes?
No.
So then, but is X bar equal to mu? I would put a lot of money that it ain't. So in a way, it kind of makes sense. I want to sort of make this range around it. But then the question is, how far do I go? What's that based on? You guys have all seen. Let me ask you this one. How many of you guys are at all like I mean, not even into politics, but just aware of it? For example, before the last election, did anybody happen to see or look up polls?
Yes.
And it said like, it looks like 48% are gonna vote for this person and 47% gonna vote for this person, yeah? Did you ever notice at the bottom, it says plus or minus 3 or 4%?
Yes.
Anybody ever notice it? Why is that there?
Is it calculating for?
Well, on one level you would say, it's because somebody, they're like counting, they're like, oh, certainly, well, that's plus or minus 4%. Cover our ass. So everybody pays attention to 48 to 47, like, oh, this guy's gonna win. But then the bottom's like, plus or minus 4. So it could really be 51-44, couldn't it?
Oh, because it's like you're saying.
So on one level, that's so much bullshit, because the more we do that kind of thing, the more we turn off voters, because they see it and they think, oh, it's done. It's already decided, why would I vote? Do you guys kind of see what I'm saying? Which is silly as shit. Which is why this plus or minus 4 should really be the first thing. It should really be like, we're within 4 confident of the, that should be what they lead with, not like a little, oh, by the way. Right? Are you guys at all with me? So anytime you see that, and again, one of the major things I want you to come out of this class with, if nothing else, is what to look for to verify what you're being told. Yes? Yes?
So like that plus 4%, whatever, like you're gonna give us a range.
Yes. So if you see, for example, if they say candidate T versus H, yes? And let's say they were saying that 48% we're going to vote for T and 46% we're going to vote for H, yes? Just randomly picking letters. And now at the bottom you see plus or minus 4%. So then this is really 44 to 52%, yes? And this is really 42 to 50%, yes? So it could actually be this. Do you guys see that? It could actually be 44% seem to be voting for this guy and 50% seem to be voting for this person. Do you guys see what I'm saying? That is, on one level, that only makes sense. Because has anyone ever called you and said, hey, who are you voting for? Has anyone ever called anybody in here and said, who are you voting for?
Yeah.
Yes?
Yeah.
Okay, good. It's gotta happen someday.
Yeah.
I've never been called.
Really?
And they probably don't call me because they're like, oh, he's a statistician. But anytime they do this poll, where do they get the numbers from? They call people. And normally they call between 1,000 and 2,000 people. And that's how they make the poll. Are you with me?
Yeah.
What do you think controls the plus or minus 4%? What would make that smaller? Say again?
The population?
No. Am I more or less confident about what I find if I take a bigger or a smaller sample? Am I more confident? When am I more confident in what I get? A smaller sample or bigger sample? Bigger sample. If I took a bigger sample, the plus or minus 4% should get smaller, yes? Why? Because that's the amount that I think I'm off by. How do I decrease how much I think I'm off by? Take a bigger freaking sample. There is a formula for that 4%. And not surprisingly, it's based on N partially. It's got other shit in it, but the sample size will be in it. Are you guys with me so far? Today is a bunch of high-level conceptual shit, and then I want to drill it down to the actual formula we're going to use. And you guys, you've been through this with me already. We've gone to, what was it I said this semester? It was an island again. This semester is all about islands.
Oh, there was an
The island with the ages,
With the goats.
it was like this, yes? Okay. It used to be alternate universe Florida, but that was freaking people out, so I stopped doing it. Anyway. All right. I'm really sorry. We're almost to the point where we're going to get something concrete. Just wait. Okay. So coming back to this example. Oh, and by the way, let me see if I can get. You all agree that for the spiders, there is an actual average. And if I plotted every group of 34, that would be in the middle of the actual average, yes? We take a sample. More than likely, that sample will be close to the mean, yes? So if I go down 2 standard deviations and up 2 standard deviations, 95% of the time, this will be close enough to catch the actual mean. I'm hoping anything I just said makes sense. The only time going up and down 2 steps would not catch this is if my mean itself was actually 2 steps away or more, yes? If the sample mean I got was more than 2 steps away, going up and down would not catch this. Does that make sense? And that would only happen 5% of the time.
Yeah.
Okay. That is what's actually going on in the background. So let me do this before we're going to come back to the spiders in a minute. You're like, oh man, bring back the spiders. Oh, by the way, this is my linear algebra. So look at it. Okay. What is this? Oh, this is the application we must tutor. Neat. All right. What I have. Oh, come back to the spiders for a second. Could I use this in my exploration of this?
If you do it over the...
So I can't use this. So did I take a sample?
Yes.
And do we want to explore something about the sample mean?
Yes.
And weren't those the 2 triggers in order to do what?
Find the standard deviation.
Find the new standard deviation.
Yeah.
So help me out. Let's be 1.2 divided by what?
Square root of 34.
Yep. Which is roughly 0.208.
Oh, I had it. It's 0.2058. Yeah.
Okay. I'm sorry. Just to toot my own horn, I got pretty close. In my freaking head. Come on, gosh. So that is the spread of groups of 34. Okay, so just hold on to that. Hold on to that. Because what I want to do next is I want to get these 2, yes? And what do we say? I want to go up how many, roughly? I want to go up 2 standard deviations. But what would I use? I'm not going to use this. I would have to use that, yes? Because I'm talking about groups of 34 spiders. Okay, maybe. And of course I would go down 2 of these. So just to bring in, just to bring in, I don't know, your notes are going to be weird on this, I know, but I'm sorry. If I want to find a data point, what formula did I use? If I know the z-score and the mean and the standard deviation, what formula do I use? What's the backwards formula? I'll get it started.
Mean plus the standard deviation. Oh. Standard deviation.
Okay. And again, this was the definition of z-score. This many standard deviations from the mean to the data point. Yes? Yeah. Now, just looking at this piece, in general, in statistics, we don't have a freaking clue what the population mean is, correct? That kind of makes sense. That's the whole point of a huge part of statistics is,
I don't know. Let's go take a sample.
right? Said exactly like that.
Just like it.
So, if I don't know mu, what did we say was our best guess? If I don't know the average age of Grossmont, my best guess is not 0. X bar. Yes? If you don't know the actual mean, your best guess would be the sample mean. Sample mean, if you picked a really good random sample, it should be close to the actual mean, yes? Okay. Now remind me, the picture I just made, don't we want to go up and down?
Yeah.
So I'm going to go up and down. We've done this once before. This many standard deviations, but because I had to get a sample mean, since we didn't know the real mean, what has to happen to the standard deviation? Well, we just figured out, of course.
Has to be divided by the
So what this formula does is it takes the sample mean we got and it goes up and down so many steps. And then I could say, if I want to be 95% confident, Z will be roughly 2. We'll see what it actually is here in a minute. If I go roughly 2 steps up and down, I'll be 95% confident that the real mean is in this. Yes? Okay. That, believe it or not, is the formula for this thing. And what this, do you all agree this is an interval that we're talking about? It's an interval from something to something that's an interval. And it's all about a certain confidence. So being the true creative geniuses we are, math people said, let's call it a confidence interval. So this is the formula for a confidence interval for a mean. Okay, so just to kind of help with your notes a little bit, let's recapture what we know back to the spiders, which is a horrific phrase, but oh well. Back to the spiders. What did we know about the spiders? We knew we took a sample of 34. We knew that we're assuming their standard deviation is the same. And just to remind you guys, on one level that doesn't make sense, but a lot of times it does. But I want to then, the next thing we're going to do after this is say, what if we only knew S, not sigma? What's S again? What's S? Standard deviation of the sample. So what if we only knew S and we had no idea what sigma was? Now that is what happens most often. We don't know shit. Okay. On this example, we're saying we know this. And what was our X bar? It was 5.3?
Yeah.
Yeah. And we got our, before we do that, okay. We already did this, but I kind of like to put it all in one formula like this. So if I put this together, X bar, give or take Z, sigma over square root of, can somebody, how do you guys figure out, I'll tell you this right now, it's not 2. 2 is not quite right. If I'm going to figure out the Z-scores that catch the middle 95%, does that not sound at all familiar? Have we not done that before? We totally have. Can you guys take a moment and figure that shit out? Does the chart understand 0.95 for this problem?
Yes.
Nope.
No.
The chart only understands areas that are where?
Under.
Yes. So don't I want 2 Z-scores here, right? I want to know how far to go down and how far to go up. What percentage is below this guy?
2.5.
Yes, 95, 5, 2.5. Yes? So 0.025. Can you guys, don't say anything. Find the Z-score with 0.025 below it. Once you do that, I'll show you the shortcut. I'm an evil math teacher. That's how I do it. Yes?
No, but so for my, 95%, you have to, what you got, I know if I will, if you need it.
Do it again.
So the 95% is what we're using right now, or is that how?
Oh.
Usually,
95% is the most often used confidence level. We're going to do other problems where they want me to be 90% confident or 98% confident or 99% confident, right? But 95% is the most often used confidence interval.
I think it's negative 1.96.
Yes! Yay! Where am I? I'm here. Look at me. Let me write on this paper. All right. Good Lord, Jeff. So this is negative 1.96. So what do you think this is without looking it up?
1.96.
Yeah, it's symmetric. Boogie, woogie, woogie. So do you see now? I really want this to make sense. In my formulas of plus or minus, well, you can see why. Because I want to go down. I want to go up. So what's the value of Z in the formula?
No.
What's the value of Z in the formula? What did we just figure out?
5.3.
No. Value of Z. 1.96. The plus or minus is built into the formula. Did you see that? Don't put in negative 1.96 and freak yourself out. Plus or minus is in the formula because I want to go up and down. Now let me show you. This is something I call the baby chart. Do you guys see this little dude here?
Yeah.
Do you see how it talks about confidence?
How confident did we say we wanted to be? Come back to me. Stay with me.
95.
Ooh. Now, of course, I'm going to want you to be 98% confident sometimes. Because checks notes, I'm an asshole. But did we just use this to figure out 1.96? No, you guys did it here, didn't you?
Yeah.
So you can do it this way. You better be. Okay. So let's put together what we got. What goes here? 5.3. So our best guess is 5.3 centimeters because we took a random sample of spiders and that's what we got. Give or take. Because real quick, because 5.3 is almost definitely not right. So to kind of pad myself, to kind of cover my ass, I'm going to go up and down far enough to say I'm 95% confident that the actual mean. Because can we take every freaking spider in this part of the region of this really big island? Can I take, if it's just you and me,
No.
just two of us out there, and we're like, let's take every spider. And they're like, no. No. We're going to take 34 minutes. All right. What goes here?
1.96.
1.96, and then we got my, and we already did this, but be careful. I'm going to put the whole thing in here, but because what's really nice is just this. I know I already did that by itself, but it's better to do this. The number one problem with mathematics is if you round too early, your later answers are off. You don't want to round too early. Do you guys agree? One way I could say this is, I think the average is 5.3, give or take that. Give or take that. Can you guys take a minute and figure out what that is? What's the amount that I'm giving or taking?
No, 1.96.
Yes, well, 1.96 times this whole thing, yes? Isn't this what I'm adding to 5.3 and taking away from 5.3?
How do you put that into your calculator?
I don't know. Oh yeah, I do. So I got 1.96 times 1.2 divided by square root of 34. That's all I want you to do right now is that piece. And I get this.
So okay. I
403.
also messed this up. Is it to the third place round or the fourth?
So here's how to do it with these. How many places is my mean? My mean is how many places?
2.
1.
1.
1 decimal place, yes?
Okay.
So then this has got to be at least 2 decimal places. Always at least one more than this. If you want to make this 3 decimal places, that's great, but it's always got to be one more than this.
Okay.
How we doing? Now, real quick, I could have taught all of statistics using something called significant figures. Has anyone ever worked with sig figs or sig digs?
No.
Did you enjoy it?
Yeah.
Oh, sweet. Maybe I should have, damn it. Normally people don't like it that much. I'm sorry, Kelsey. Kelsey's like, you could have done that? Don't tell me that, Jeff. I'm sorry. So let's see, 0.4. So I would say 0.40. Just to be safe, I put 0.403. Just because there's an O there, right? So I love it. One semester this literally happened, which is awesome. So they came up to you and said, Jeff, where's the plus or minus button in the calculator? Is everybody cool with their reasons? What do you have to do?
Do them separate and then.
You gotta subtract one and you have to add one. Yes?
It would be smart to have in here though.
Maybe. 4.897, I think. Is that right? Yeah, neato. Go, Jeff, go. What the shit does that mean? What does that mean?
Oh, is that telling you, like, in between your two standard deviations?
How confident are we that something, that interval catches something? How confident are we? What is that interval trying to catch? What's the whole point of what we just did? The actual mean, yes? So we are how confident?
95% confident. If I wanted to be a different level of confidence, I would have put a different z-score related to that level. 1.96 is related to 95%. If only 90% confident, it would be a smaller z-score. I would catch less if I want to be less confident that I caught a specific thing. Does that make physical sense? Catch less fish, I'm less sure I caught Billy. Really? So I'm 95% confident that that interval catches the real mean. So is this evidence that the average diameter of spiders in this region is different from the rest of the island? What was it for the rest of the island? 5.
So now.
Is this evidence that the spiders in this region have a different diameter?
Yes.
Yeah.
No.
No, because it can't.
Because could it be 5? If the interval we got was 5.1 to 6, would that be evidence that the spiders have a different mean diameter? If it was 5.1 to 6, yes, because that is, the whole thing is above 5. This interval tells me, could their average be 5? Total. So is this good enough evidence that their average is not 5? No, because it could be 5. Does that make sense? Yes.
Is it because I fall catching those two numbers?
Sorry.
Is it because I fall into those numbers?
Yes.
Like 5? It could be
That interval is consistent with 5. So is it evidence that it isn't 5? No, it can't be evidence that it isn't 5, because it could be. So again, if my interval, if the interval we calculated would have been this, is that evidence that it isn't 5? Yes. What's the probability we would be wrong? 5% chance.
So that just told us 95% of the data, yeah.
So we are 95% confident that the spiders in this region
Are consistent with the spiders in the rest of the island. Did we get close to having an interval above 5? So if I was really certain, I'm like, no, I think that's wrong, I would go take a bigger sample. Maybe the sample we took, again, didn't really represent. You guys know, plus if I take a bigger sample, I'll be more confident about what I get, correct? You guys at all with me? A little bit? So, real quick, this is better than just saying we got an average of 5.3. This is communicating to somebody how certain we are about what we got. Instead of just saying we got 5.3, doesn't tell. If I say we think it's between 4.9 and 5.7, that tells me a lot more information. Yes.
I was wondering, can you repeat the part, like, this is not evidence that the population mean is 5?
This is not evidence that the population mean is not 5. Yes. If I'm trying to show that the spiders in this region have a different diameter, this doesn't do it. Because is the actual average for all spiders in there? Yes. What would have been evidence
would have been either something like this or something like that, right? This would have been evidence that they're a larger diameter. This would have been evidence they're shorter diameter. Yes? Because this is completely above 5 and this is completely below 5. And again, there's a chance that we're wrong. That's the reason people don't like statistics. And to me, that is stupid. Statistics is the most honest math. It goes, I think it's this, I think it's this. And that's freaking life. That's freaking life. People give up on stats because they're like, oh, stats is not going to tell me the next winning lottery number. Nobody can, get out of here. Get out of here. What the hell do you want from math? So stats to me is beautiful because it's very honest. And the most we can do in almost every situation is say, I'm pretty confident. You can't ever be 100% confident, right? Just to be morbid for a second, the sun could not come up tomorrow, right? I mean, it could just blow up. There's a chance of that. So you can't be 100% certain you're going to see the sun. Ooh, Jeff, great. Good job, Jeff. Earthquakes, spiders, sun ain't going to come up.
Are you okay?
No.
I'm fine. Okay. Unless giant spiders come and there's an eclipse and the earth shakes, then I might not be so worried. All right. So what we have is if I ask you, here, let me ask you this. If I want you to make a confidence interval, and confidence interval from here on out is gonna be CI, okay? Because the less I write, the better for everybody. If I want to be 95% confident what z-score we're going to use, we just use it. 1.96. Can somebody do something I just showed you how to do earlier and tell me if I want to be 90% confident what z-score we'll use? Can you find that very quickly? 1.645. And again, it's what I call the little baby chart. 90% confidence level, 1.645. Let's verify that shit. Can you guys draw a 90% confidence interval for me? I'll start it. So now you see why I asked you this. Between what two z-scores do we find 90% of the blah, 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 blah? Remember that question? Because I'm getting you ready for this shit. So between two z-scores, I find 90%, yes? How do you figure out those? Well, chart doesn't understand this shit. What percentage is out here?
5 and 5.
Yeah, 5 and 5, yes?
Yeah.
If you try to find 0.05, you're gonna get that little asterisk dude we've seen before, and if you follow it, sure enough, it's 1.645. Now, everybody take a moment and figure out if I want to be 96% confident. What would the z-score be? Don't say anything. So that was for 90% confidence. I want 96% confidence. Let me see if I can do this really quickly. I want to show you some actual shit. No, not actual shit, but like actual study. There it is, Jeff. Yeah, okay, that's right. I think, yeah. Bum, 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 bum. Out of sight. Out of sight. Fudge. Give me what I want. Come on. What is going on here?
So you
No.
have to get as close as possible, right?
Yes. Come on. Wait, why is this not working anymore? Come on. Come on. Okay, here we go. Oh my god, that's from 1,000,000 years ago, but that's okay.
So 2.05.
Ooh, dissension. Okay, my computer just died. Yay. What happened? Okay. Oh. What just happened? Did you die? Oh, maybe you died. That's interesting. Oh, that doesn't work. Backup mouse. Yay. Go away. Sorry, guys. I'm trying to find an actual study and I'm having trouble. Let's do this. Bam, 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 bam. Oh my god. Oh, okay, perfect. I know where to go. Sorry. News, there it is. Kind of boring, but too bad for me. Come on, you could do it. You could do it. There you go. Internet, kind of working. Do. You suck. Do. Why aren't you giving me what I want? Did anybody get that, by the way? I'm sorry. What'd you guys get?
I got
I'm sorry, do it again.
Negative 2.88, 2.255.
That is way more than you should have gotten. The Z-score chart only goes out to 2 places. I have no idea how you manage that.
1.7. But I got 2.05.
So let's think about this. In order to be 95% confident, how far out do I have to go? We got that. First thing we got. What is it? 95% confident, how far out do we have to go?
2.5 on each.
You can do it. We already did it. It's the first thing I listed it, right above that. I'm not even going to pull it down. 95% confident, how far do I go? No. We know more specifically now. We don't have to rely on empirical rule. We know exactly. It's 1.96, yes? If I want to be 96% confident, don't I have to go out a little further? If I want to be more confident, should I catch more stuff or less stuff? I should catch more stuff to be more confident that I caught a specific thing, yes? So if 95 takes 1.96, it makes sense to be 2.05 to be 96, and that is right, it's 2.05. How do you find 96? If they're 96% inside, how much is outside?
2%.
Because they know exactly what you did in Arizona. 96%, there's 4% outside, correct? 2%, so look at 0.02, not 0.04. I'm pretty sure that's what you did. Oh, interesting. Let's look at this. Please tell me what I want to know. You jerk. Are you really not telling me? Sorry, guys. Bless you. Here we go. No. Everything's let me down. I don't believe this. Why is everything let me down? This doesn't make any sense. Why don't you guys... Here we go. Okay, thank God. Okay. Sorry. I found it. So 2.05, yes. All right, so let me show you what I just found. It's not very... So this is a study at Gallup about most schools in district last year. Blah, 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 blah. So defining quality is hard, making math progress harder. So you could read through it if you wanted to. And they asked, how familiar are you with the concept of high quality instructional materials? Blah, blah, blah. So they go all through this and they explain what they found in the sample they took. Blah, blah, blah. But if you go down to the bottom, there's a survey methods thing you can click, and they tell you how many people they talked to, how they picked who they talked to. These are the things you have to be able to find. And more importantly, look here. Plus or minus 3 percentage points. I don't know if you guys can see that. It's really tiny. You could do this, Jeff. Ooh. The margin of error is plus or minus 7 percentage points. For principals, it is plus or minus 3 percentage points, blah, blah, blah. Ooh, look. Ah. Sorry, I just want you to, it's always nice to know, especially in statistics, it's easy as shit to do this. Go out to any study and you can find exactly what we're talking about. They calculated a confidence interval and they figured out how far they were off. That's why it's plus or minus, right? Okay. I'll stop. So let's do one problem and then we'll head out. Let's say I want to know the, on this island, we find another island next to the first island with the spiders. And on this island, there's no spiders, thank God. But There's a species, there's a certain genus or whatever the right word is of bananas. Bananas. And we're curious if it has a higher potassium level than normal. Is everybody with me? Okay. And we know the standard deviation of bananas all across the world, potassium level is 0.914. And I don't know what the units are because I'm just making the shit up. Yes? I don't know if you guys noticed, I did not go to an island and take a bunch of bananas just now. Oh, yeah. Let's say we take a sample of 57 bananas, and we get a sample mean of, what do you got, Jeff? Let's say 5.03 units of potassium. Yes? Potassium. That's what's in bananas. Okay. So we want to be able to report what it seems like the average amount of potassium in bananas is from this island. And if it's statistically shown to be higher than the bananas here, then we can go out and make a commercial. We could say, come get our bananas, has been clinically proven to have more potassium than your normal banana. It tastes like shit, but still, you know. Sorry. By the way, real quick, I don't know if anybody's ever been in Hawaii. If you ever go, eat as many bananas as you can. They are like good. They are silly good. So I'm always like, I miss my bananas from Hawaii. They're sweet, but there's something different. It's just, bananas are good, but Hawaiian bananas. Now, of course, they have, fertile soil, volcanic stuff. Everything tastes better, but so good for them. So let's say I want to make a 98% confidence interval. Number one question that I haven't really brought up, except for a little bit at the very beginning. Why will you be able to look at your z-score chart for this? Don't say because I have eyeballs and you gave me a chart. For this one specifically, 57 bigger than 30. So I know that if I plotted all the groups of 57, it would be normally distributed. So I'm allowed to use the z-score chart because, like Steven said, normal enough is good for everything. So this is very often one question I ask you is, why the shit are you allowed to do what you're about to do? Bless you. What if n is not bigger than 30? What do I have to say in order for you to be able to continue? It's already normal. So I only need n greater than 30 if I have no idea if it's normal or not. I need something to save my ass. If I say it's normal, I don't care if I make n 7. It's already normal. Okay, this one wasn't. That's bigger than 30. I'm allowed to continue. Has anyone found the z-score I need yet?
2.33, right?
Yes. So if you look up, sorry, go ahead. Oh, all right, so 90% inside, how much is on one side? 1%, right? So if you look up 0.01, where are my glasses? Since my baby left me. Right there. That's the closest I can get, 2.33. I don't care about the negative sign because the plus or minus is built in. So do I have everything I need for this formula?
Yeah.
Yes. I got the x bar, I got the z, I got the sigma, and I got the n.
Gonna be so real with you. I was looking at the work we did previously, so I put the wrong standard deviation. So I was looking at the past problem as I was doing it, so I put 1.2, but I did it.
Gotcha. So what's the first piece of this you want to do? In fact, let me point this out. Not surprisingly, by the way, real quick. Have you ever gone to like well, I don't think they had this at the fair here, but when I was a young boy growing up in Georgia, we would go to these state fairs or whatever, and there would be somebody in there that would be like guessing people's weight.
Yes.
And they would say, I'll guess your weight to within 5 pounds or whatever.
Yeah.
Within 5 pounds, plus or minus 5 pounds. That's how much they were allowing themselves to be off by. That is how much they allowed their error to be. So we call that part of it the error. How far off we are. That is give or take. That's what we call the error. Error. So you normally calculate that first. In the book, they'll often ask you what the error is, so you want to calculate this first anyway. So anytime somebody does that, let me think. Wait, don't say anything. I think it's about 0.3. Yeah. I'm going to say 0.3. What is it? 0.2 what? 0.28. That's not too bad, Jeff. By the way, real quick, what was the next? 2.8 what? 2.82? Okay. If you're playing along, is that what you got? Is anybody else playing along? Did you just wait till somebody did it? Like, somebody's going to do it.
Oh, that was.
That's the error. Yeah, that's how much this is. All right, I'm going to go with that because that sounds right to me.
Yeah.
So if you add and subtract this from this, what do you get? I don't know.
4.7.
Thank you. 4.748?
Yeah, and then 5.312.
Now let's say that the mean potassium level in bananas in the States is 4.5. What will this study enable us to say in our commercial?
This is like the mean everywhere else.
That's the mean of bananas in the States.
So they would say their potassium is higher.
Yep, we say it's been clinically proven. And nothing can be proven. So when they say clinically proven, they mean enough evidence has been found. So you've seen these commercials.
It's been clinically proven that our pain reliever relieves your headache faster.
Plus your shit. So they took a sample and they said, oh look, the confidence interval is above that, so let's make a commercial. Yay. You guys kind of with me?
Yeah.
Is it possible that what we're claiming is wrong?
Yes. No. Because we just proved it.
We didn't prove shit. What's the chance that we're wrong?
Oh, 5%.
2%.
I don't know.
We still could be wrong, yes?
Oh.
But it's only 2% chance. So if the FCC or something actually try to come down on us, we're like, they didn't really come down. They just, we can say that shit. Clinically proven means something very specific, and people don't stop to think about it. You just think, it's definitely going to do that. No. They just shown evidence. It doesn't mean it definitely will. But we can do it now. We can make commercials for our little bananas. Get past the taste. Get more potassium. Okay, sorry. All right. Don't get used to this. That's plenty. That's plenty. So next time I'll have what do you call that? A worksheet we'll do that covers this. We'll get into section 8.3 next, and then we'll do 8.2 after that. Because there's a whole different chart, a whole different
So our last day of this class is finally.
Yes.
May 7th.
I can't remember. No, I don't think it's May 7th. There's no way it's May 7th.
May
Don't get too excited.
May
The end of May is supposed to be. I want to take it personal that you're